The number of cracks in a section of interstate highway that are significant enough to require repair occur with an average rate of 2.3 cracks per mile. What is the probability that there are no cracks that will require repair in the next 5 miles of highway? Okay, so we've got a rate, lambda, and that is 2.3 cracks per mile. Okay? And we want to know what's the probability that there are no cracks being required to repair in the next 5 miles. So x here is going to be a random variable that counts the number of cracks in 5 miles. Okay? Naturally, our rate and our random variable have to agree with each other with respect to the interval. So this lambda here is going to be 5 times 2.3, which is 11.5 cracks per 5 miles. Okay, so our rate, 2.3 cracks per mile, is equivalent to 11.5 cracks per 5 miles on average. And we want to know what's the probability that we see no cracks in the next 5 miles. Okay, so what's the probability that our random variable takes on the realization 0? Okay, straightforward. We've got a rate, 11.5 to the 0, e to the minus 11.5 divided by 0 factorial. And as it turns out, that value is 0.1003. Okay, so on average, 10% of the 5-mile stretches that we might encounter will have no cracks that need repair. Okay, we'll move on and ask another question. What's the probability that at least one crack requires repair in a half a mile of highway? Okay, so let's change up our lambda. Lambda was 2.3 cracks per mile. And we need a half a mile as our interval. So that would be half of this, 1.15 cracks per half mile. Okay, and our random variable, let's call it y, is going to be the number of cracks requiring repair in half a mile. Okay, and so now we want to know what's the probability that at least one crack is going to require repair in the next half mile. That's the probability that y is at least 1. Okay, at least one or more, inclusive of 1, cracks in the next half mile. Okay, that's the probability that y equals 1 plus the probability that y equals 2 all the way to the probability that y equals infinity. Okay, because we are not bounded on the upper side for this random variable. In theory, we could have 1 million here, we could have 18 million, whatever it might be. We don't have an upper bound on a Poisson random variable. You could spend a lifetime solving this problem. Or we could think of it this way. What are the possible realizations of this random variable? 0, 1, 2, 3, all the way up to infinity. And we want 1 or more. Okay, that's translating this into this kind of statement says this. So we could solve this by taking the complement of the probability that y equals 0. So the probability that y is greater than or equal to 1 is the complement of the probability that y equals 0. Okay, that is 1 minus our rate, which is 1.15 to the 0, e to the minus 1.15, divided by 0 factorial. And if we work that out, we should get a probability of 0.6834. Okay? So the probability that we see 1 or more cracks in the next half mile, 0.6834. On average, we'll see 68% of 1/2 mile stretches that have 1 or more cracks.